Greetings and welcome to this video in our series covering strength of materials and mechanics of materials. This particular video will consider torsional shear stress and the angle of twist. So if we go to a diagram of a simple circular tube, we can assume that the tube is being twisted. There's a torque on this side and an opposing torque on this side. This will induce a shear stress and will also cause it to have a deflection in a twisting fashion, so it's an actual angle. It's a little bit hard to show here, but all you need to do is pick up a pencil or a paper clip and twist it yourself, and you will see that with a torque you will induce shear stress, possibly enough to break the pencil, and you will also induce an angle of twist. So the formulas regarding these two concepts are fairly straightforward. So for our torsional shear stress, and shear stress is denoted by the Greek letter tau, we multiply the torque times the distance from the center to the outermost fiber, C, I'll show you what that is in a little bit, and divide by J, the polar moment of inertia. For the angle of twist, theta, we start off with the torque again, multiply it by the length of the shaft, and divide it again by J, and also G is on the bottom. G is a material property, so we'll get into that. So T is common to both. It's very important. It's simply the applied torque. This may be given to you in a problem, or you might have to solve for it using other equations. Another video will be showing you how to do that with power transmission. C is distance from the centroid of the shape to outermost fiber. Okay, this outermost fiber of a cross section is going to undergo the highest shear stress. So that's why this is the maximum shear stress. And for a circular shaft like I was showing you, it is simply the outer radius. If it was, say, a square shaft, which is possible, it would be this distance from the center of the square to the corner here. But very often these drive shafts or other shafts that are designed to take torsion are circular because it's a very efficient shape for that. Okay, moving on, J. J is the polar moment of inertia. There are many formulas for that depending on the cross section as well. For a solid shaft, J is pi d to the fourth over 32, or for a hollow shaft like we were looking at, it's the same thing. It's pi d to the fourth over 32. You just have to subtract out the middle. So you use the same formula over again, or you can simplify it in this way. D to the fourth minus the internal diameter to the fourth over 32. So this is small d, and this is large d. That's the outer diameter. So these are to the fourth. Now note very importantly that each one here is raised to the fourth power. If you tried to simply subtract the two and raise it to the fourth power, that would be wrong, and you get the wrong answer. So it can be a very large difference between those two. So make sure that you use d to the fourth on each one individually. An easy way to do it on your calculator is to type in, say it's 1.5, right? Square it, square it. So you use your square button twice, and that will be the same thing as 1.5 to the fourth. Okay, you might want to play around with it depending on your calculator, but that's what I do. I just hit squared twice. So we've got T, C, and J. So T and J are covered here in the angle of twist, and L, pretty easy. L is the shaft length, and G is the shear modulus of the material. In a different video, I go over how G is related to the modulus of elasticity, and there's a formula for it, and you can look that up, but it might be listed in a website, or you might have to calculate it, but the calculation's not too bad. Okay, one more thing about this that you got to remember is that this angle is in radians. So if you want it in degrees, you have to multiply times 180 degrees over pi to get degrees. Okay, because there are 180 degrees in half a circle and pi radians in half a circle, or 2 pi for the full, 360 for the full, but just cancel them out. So just make sure that when you get a really small number for your angle of twist and you're wondering why it's so small, it could be that you haven't converted it into degrees. All right, let's do a problem that covers these things. All right, so let's find out what's given. All right, given is, and we have a hollow circular shaft, just like what I was showing you before, and it's a drive shaft. This means that it is going to be subject to a lot of fatigue and possibly some shock, and so a variety of loading. So it's going to undergo a lot of loading. So we've got outer diameter of 1.25 inches and an inner diameter of 1.0 inches. We have a length. If you'll notice on the diagram, we've got 1 inch on the inside, 1.25 on the outside, but well, I did it this way because otherwise it wouldn't fit on this screen very well. But just remember that this is feet. Okay, next. So that's 6 feet. And we are taking a torque of 50 foot-pounds. And our material has already been chosen for us. We're already told that it is going to be 4140 OQT 900. Now, if you have the Mott book, this is listed. If you don't, well, I'll show you what it is in a second. We're supposed to find a couple things. A, shear stress developed here, and also check to make sure that the applied shear stress is less than the ultimate strength divided by 12. Okay, so we have a design factor equal to 12. In part B, find the angle of twist, and make sure that it is less than equal to 5 degrees. Alright, so let's get moving on part A. For A, we want to calculate the shear stress, so we use that cool formula. Tau equals TC over J. You know, I'd forgotten I was going to change that from 50 to 250 foot-pounds. So when we do the problem here, we'll make it 250 foot-pounds. A little bit more realistic. So let's write down what we've got here. Torque equals 250 foot-pounds. C is the outer radius, so we just take the outer diameter and divide it by 2. So it's 1.25 inches over 2 is 0.625 inches, 5/8. Jay's going to take another calculation. But because we're going to use it in part B, we may as well calculate it by itself. So J is pi times the outer diameter to the fourth minus the inner diameter to the fourth all over 32. So this is pi times 1.25 inches to the fourth minus 1.0 inches to the fourth all over 32. And when that is all plugged into the calculator, we get 0.1415 inches to the fourth. So let's plug this in and see what we get. Shear stress equals 250 foot-pounds times 0.625 inches all over 0.1415 inches to the fourth, and that comes out to a stress of 13,250 psi, or 13.25 ksi. Now, if you'll notice, I added this down here. We had to look up the material properties for the 4140 OQT 900, and I found it in the back of the book, which kind of looks a little bit like this. And so here it is, 4140 OQT 900, and we have an ultimate strength of 187 KSI. Also shows the yield strength and the percent elongation. So the other thing we needed to find for the angle of twist is this G, the shear modulus. Well, if you'll notice on that line, it's not there. This confuses some students, but if you simply read the entire chart, you'll find that it says other properties approximately the same for all carbon and alloy steels. So the modulus of elasticity and tension, so that's E, is 30 million psi, and the modulus of elasticity in shear is 11.5 million psi. So I wrote it down here as 11,500 ksi. Probably write it in here as the 11,500,000 psi. But we'll get to that in part B. So after all that, we've got 13.25 ksi. Now we want to compare it to the ultimate strength divided by 12. For that we get 187 ksi over 12 is 15.6 ksi. This comes out pretty well because that is our allowable stress, and we don't want to go over that. Well, our applied stress is 13.25 KSI. And so if that's what we're working at and we're underneath this allowable stress, we're good. Okay, on to part B. For part B, the governing equation is that our angle of twist is the torque times the length over the polar moment of inertia times the shear modulus. And we'll just plug these right in here of 250 foot-pounds times 6 feet all over J, which we calculated out here to be 0.1415 inches to the fourth, times G, which is 11,500,000 psi. I'm going to change that to pounds per square inch. You'll see why. And then I've got feet here and feet here, so I have to multiply by 12 inches per foot twice. Okay, let's look at the units here. We got feet here, cancel those out. Okay, pounds on top, pounds on the bottom. Now this down here we've got inches to the fourth on the bottom, but inches squared is on the bottom. So that cancels that out to 2, and then I've got inches here and inches here. I've got 2 of them up there, got 2 of them down here. They cancel out, bam, bam, and we end up with a unitless value, which is exactly what we wanted, which is radians. Radians is a unitless measure of angle. So after all that's said and done, we end up with 0.133 radians. This is radians, not degrees, and we were told that we need to have an angle of twist less than or equal to 5 degrees. So we need to multiply that out times 180 degrees over pi radians, and we end up with 7.6 degrees. This is greater than 5.0 degrees. Not good. Okay, so what are we going to do? Well, let's just assume that we already have this material picked out for one reason or another. Changing the material, assuming it's steel, is not going to do us any good because the only thing that's going to change is G. As we saw here, they're approximately the same for all carbon and alloy steels. G is the only one that's considered in this angle of twist, so G is not going to change. So changing the material isn't going to help. Changing the outside diameter might help, so we would have a larger J making a smaller angle. However, the design is such that maybe this has to fit in a 1.25 inch receptacle somewhere. So changing the outside diameter could affect the design of other parts. The length, well, probably has to fit between two things, and maybe we don't want to change the design of those other things. So what can we do? Well, it's got to transmit that torque. There's not a lot that we can do here. We've got one thing I can do, and that is reduce the size of the inner diameter here. If I reduce that inner diameter, then the value of J goes up. The question is, how much will it go up? So let's try to choose something a little aggressive. So let's change D to 1/2 inch instead of 1 inch. That will give a lot more rigidity to the shaft so that it won't twist as much. So assuming that nothing has to fit inside the shaft, but we'll still see how this works. So that is going to change J. So pi d to the 4th minus d to the 4th all over 32. So it's pi times 1.25 inches to the 4th minus 0.5 inches to the 4th over 32. And our new J is 0.2335 inches. To the 4th. Our new angle is, keep everything else the same, 250 foot-pounds times 6 feet all over 2335 inches to the 4th times 11,500,000 psi. I've done the units on this before, so I'm not going to worry about it again. Times 12 inches per foot, twice. I end up with a new angle of 0.0804 radians, and then I multiply it by our conversion factor, and I get 4.6 degrees, and that is less than 5.0 degrees, so we're good. Just to go back to our shear stress, let's find out what the new shear stress is going to be on this new design. So for our shear stress with D equals 1/2 inch equals TC over J, 250 foot-pounds times, C hasn't changed because that's to the outer, so 0.625 inches all over 0.2335 inches to the 4th gives us 8,030 psi. Now if we compare that to our ultimate strength, we take 187 KSI, divide it by 8.03 KSI, which is from here, we end up with a factor of safety about 23, which is double what we were originally, almost double what we were originally looking for, which was a design factor of 12. Okay, so you might consider maybe changing the material to something a little bit cheaper if this is expensive. Maybe if you wanted something else, maybe a little bit more ductility, whatever. But this gives you, with regards to strength, a little bit more flexibility. Okay, for this particular lecture and problem, we considered torsional shear stress, discussed a little bit about what it was, and introduced the equations, and went over what the different variables were and some of the pitfalls that I hope you can avoid. Then we had a problem where we were given a drive shaft with various dimensions and a material choice. We had to look up some stuff for that material choice in order to find the shear stress and check that the applied stress was less than the ultimate strength over 12. And then we found the angle of twist. So we went over that and one by one got those particular variables, plugged them in, found out that our shear stress was good, but our angle was not so good. We changed the dimension of the inner diameter, and that changed our polar moment of inertia to something large enough so that our angle of twist got under 5 degrees, and then we checked our factor of safety again. I hope this video has helped you understand more about torsional shear stress and the angle of twist, and what factors affect the shear stress and angle of twist, and how we can calculate them and find them and look them up, and what kind of effect that might have on various parts of the design. Thank you for watching, and as always, give feedback if you have any suggestions, and I hope you do well in your studying of strength of materials and mechanics of materials.